So now the answers for the aspirin part, and we'll start off with our data. If you remember, we took some of our sodium salicylate solution, which we then diluted to varying amounts, each time diluting it to a total of 12.5 cubic centimeters. So here we took 0.5, 1, 1.5, 2, 2.5. And the starting concentration for each of these then, starting concentration of the sodium salicylate, you might remember from the calculations going through, 8.69 times 10 to the minus 3 moles per cubic decimeter. First one, we took 0.5 cubic centimeters of that and diluted it to 12.5 cubic centimeters. So what was C2 in this particular case? It was 3.48 times 10 to the minus 4. And on the original movie, I had a little arrow pointing to this box. Anyway, then doing the calculation 4 more times, each time putting in the appropriate volume of the sodium salicylate solution. So 1 goes there, then 1.5, then 2, then 2.5. Again, cunningly, it was all set up so that the total volume was always 12.5 cubic centimeters. So when I calculate those concentrations, I get these values. Okay, and again, all I'm doing here is I'm just doing the same C1V1 equals C2V2 calculation. This one being the V1, C1 being the 8.69 times 10 to the minus 3, V2 is always 12.5, and C2 is listed here. Putting that into the next chart, which is showing us Beer's law. Absorbance is epsilon L times the concentration. Well, there's the absorbance, there's the concentration. Two ways in which one can use this equation in order to get essentially the conversion factor, epsilon L. First way to do it is, I think, the tackier way to do it. You just use these data, pop them in to this equation, and rearrange to get epsilon L. So 2.62 for absorbance, 3.48 times 10 to the minus 4 for the concentration, gives me 753. Do that calculation 5 times and average it, and I get 703 for the epsilon L. Now I'm going to anticipate a little bit here, and I'm going to say that when you look at all these data, this really is a pretty tacky odd one out. And so remember that third set of data, right, the one that has the 1.04 times 10 to the minus 3 concentration, about 1 times 10 to the minus 3 concentration. Remember, that's rather tacky. Now if I take that out here, my average epsilon L is 722. Okay, now you might ask, why didn't I also take out the 753, which is also kind of well away from 712, 716, and 704? Well, the answer to that comes from when you do this in a little bit nicer of a way, and you plot the graph. We plot absorbance along the y-axis, concentration along the x-axis. Well, then the slope of that line should be epsilon L. It should give us a straight line because absorbance and concentration are proportional. Should give us a straight line with the slope being epsilon L. Now here's the line plotted out with just the data points. You can see that middle point there, pretty ugly. If this is the standard line I use, you can see that third point, the one that's just a bit bigger than 1 times 10 to the minus 3, kind of out the way. Now, I can always, in a nice graph like this, remind myself that if there was no concentration of my colored solution, I would have 0 absorbance. And indeed, if I calibrated the machine correctly, that would be the case. So I will always say, think about whether or not you can put the origin in. And in this case, absolutely I can. If I had none of my sodium salicylate solution, I wouldn't have seen any absorbance at that particular wavelength, and that is how I would have calibrated it. So now I've got a 6th data point that I can add, and again you can see that middle one there, the 1 times 10 to the minus 3 value, kind of still popping on out. So I'm going to remove that. I'm not going to remove any of the others. The rest look pretty good, but that one, once you see it graphically, is obviously out of whack there. And so by leaving it out, I get a glorious straight line. As slope of that straight line, 704.04, and there's a teeny little correction factor of 0.0078. So you can kind of think of absorbance is epsilon L times concentration. Epsilon L is 704, call it. So absorbance 704 times the concentration plus teeny amount, 0.0078. Now remembering all this, let's go to the questions. Misspoke ever so slightly. Before I get to the questions, let's bring in the unknown data. If you remember what I did, I crunched up an aspirin tablet, dissolved it ultimately in 250 cubic centimeters of solution, and then took 3 samples of that, which I treated in exactly the same way I did with the sodium salicylate solution. In other words, dissolved it up, react it with Trinder's reagent to make that nice, pretty iron complex, the purple iron complex, and I did that with 3 tablets. So I have 9 bits of data, and the average absorbance 0.272. So now going to the questions. What was the average absorbance? 0.272. Now, using my value of epsilon L, what was the concentration then of the solution of the unknown? And again, absorbance, which I got there, epsilon L, which was about 704, concentration unknown, pop all that in, and I get that the concentration of my solution, 3.86 times 10 to the minus 4 moles per cubic decimeter. And that's effectively the concentration of the sodium salicylate in that unknown solution. Now, 1 sodium salicylate comes from 1 aspirin. So what was the concentration of aspirin in the unknown 250 cubic centimeters solution? Well, let's see. I took 2.5 cubic centimeters of that solution and diluted it with 10 cubic centimeters of Trinder's reagent and measured that absorbance. Okay, so therefore using C1V1 equals C2V2, my measured concentration, 3.86 times 10 to the minus 4 moles per cubic decimeters, was the concentration in 12.5 cubic centimeters of my diluted solution. But what I want is, what was the concentration in the 2.5 cubic centimeters? So C1V1, this is the diluted solution, this is the original solution. C2 was equal to 1.93 times 10 to the minus 3 moles per cubic decimeter. So what's the mass of aspirin in the original 250 cubic centimeters of solution? Well, the original 250 cubic centimeters, the concentration, 1.93 times 10 to the minus 3 moles per cubic decimeter, but I only had 0.25 or I only had 250 cubic centimeters or 0.25 cubic decimeters, so I have to multiply that by 4 to get 4.825 times 10 to the minus 4 moles of aspirin that were in that 250 cubic centimeters. Aspirin has a molar mass of 180 grams per mole, so 0.087 grams of aspirin. And then finally, the easiest one, if the tablet weighed 100 milligrams, what's the percentage aspirin in those tablets? Well, 1 tablet went into that 250 cubic centimeters of solution. We found out there was 0.087 grams of aspirin. So therefore, the percent aspirin, 87%, 13% filler of some kind or other. Hope that made sense. Hope you enjoyed it. Let me know any comments or questions. Bye-bye.